evaluating the sense of temperature changes using a special nerve in our body called the trigeminal nerve. So this work was done in collaboration with my colleague Stephen Noggles, who's not here with us right now, and my advisor Pedro Lopez, who is, hi Pedro, at the University of Chicago. And I'd also like to start thanking the CHI community in general for receiving a Best Paper Award. We're super honored by the recognition. So let's start with a teaser. So today what we'll be talking about is kind of how this person is actually feeling a sense of temperature using a pretty low powered device that we built specifically for this kind of effect. Now this work was motivated by the fact that there's an increased sense of realism in virtual reality. So here I whipped up two different scenes that are already fairly photorealistic. And this is in addition to like visual realism. Industry and researchers have been kind of exploring new modes of realism for virtual reality, such as consumer solutions for rendering touch, or things like rendering forces, that's the Dexmo, as well as researchers exploring ways to render odors or even temperatures for virtual reality. So I'll go over how researchers have begun creating these kinds of thermal feedback in VR for consumer headsets. Now, the most straightforward approach involves heating lamp/air conditioning units to change the temperature of the air itself. This can be found in some custom VR arcades like the VR Sense. The downside is that these devices require a lot of power and end up being big, which runs completely contrary to what people are interested in these days, and especially the commercial industry that's moving towards untethered devices. In fact, VR's biggest promise is small home setups or portable systems, such as the Oculus Go, and at this point, most people are probably familiar with the Oculus Quest that's on the right. In the end, it's all about giving users a sense of mobility and staying untethered. Now, researchers have been able to miniaturize thermal feedback and have most recently turned to these things called thermoelectric materials, also known as Peltier-elements, to do so. These are useful because they can be small. Essentially, passing a current through the element creates a temperature difference across the two surfaces. One side gets cold and the other gets hot. Unfortunately, to create the temperature difference and sustain it, an equivalent amount of power is needed, and that can get pretty costly. That means these devices are small, but they still remain tethered. So let's take ThermoVR system based on Seto and Maeno's method for a fast temperature switching system. To sustain this kind of 10-minute full frontal cold sensation using thermal VR, 10 Peltier modules would be actuated to cool the skin down by 3 degrees Celsius, and each would need, in the worst case scenario, 0.5 amp hours. Putting that all together, for a 10-minute experience, we have 4.78 amp hours of battery being used. And this doesn't take into account like something that's optimizing for skin temperature. That's already 1.5 times your iPhone 11 battery. That's a huge amount of power to kind of walk around with to create these sensations. In other words, our goal in this case is to bypass that need for lots of power, which means you can't address this problem with a solution bounded by traditional physics. So we turn instead to thermal illusions, relying on chemically actuating our senses. To do this, we focused on the chemical senses of the face, and especially we focused on the nose. Now, most people are probably familiar with the tongue, which is responsible for taste, as well as the olfactory bulb, which reacts to odorants, which creates a sensation of smell. Now, there's a third one that you probably are not so familiar with called the trigeminal nerve. Most people actually associate it to the first two. So when you're eating or smelling something, and you can actually recognize it with sensations like seltzers or sparkling beverages, the bubbliness, that's going to be a trigeminal sensation, sparkly things, spicy things, refreshing sensations. Now, what's neat about this is that you can actually activate this nerve with mechanical deformations, and it also has receptors that respond to temperature changes. So for example, if you're walking outside at negative 10 degrees Celsius, like it is most of the time in Chicago, you know that refreshing feeling that when you breathe in, that crispness, that's in fact your trigeminal system responding. Now the trick is that these receptors that respond to temperature changes of the tissue also respond to chemical stimulation. So it begs the question, can we actually elicit those feelings with chemicals only? Of particular interest to us was two receptors. There's the transient receptor cation channel V1, which is the top one. You don't have to memorize the full term, just TRP is a good way to abbreviate it. So V1, that's at the top, and then M8, that's at the bottom. Now, both of these TRP channels are temperature gated with respective thresholds. And of interest is that you can also chemically activate them, notably with two extracts commonly found in plants, capsaicin for peppers and menthol for mint. And to clarify, these receptors are gated by temperatures of the surrounding tissue, not the air. So if your body gets to like a 45 degrees Celsius temperature, that is incredibly hot for your tissue. And same thing, like 25 degrees Celsius of the tissue is actually very cold. Now, in our case, we started looking at this by first working with essential oils, which some people are a big fan of. Now, to explore this, we actually implemented a prototype thermal display that's in fact an untethered olfactory display. So olfactory display is a smell display for people that might not be familiar with those terms. Here we're using a phone to actually activate an emission of the aerosols. So the chemical compounds in each channel. And we created the device by combining a Bluetooth microcontroller, a couple of micropumps, some reservoirs to keep the chemical compounds, and then a mesh atomizer to create an aerosol. Now, what's cool about this is that we can do things like emit capsaicin to create a warming sensation by just pumping some of the compound from the reservoir to the back of the atomizer. And similarly, we can do things like create a cooling sensation by emitting eucalyptal, which is another compound. Finally, we can also do things like mixing. So we can mix capsaicin at temperature in some sense, with a floral accord, so like a flower smell, and that probably have smell and temperature at the same time. So to ensure the device's success, we had to address a couple different problems. First, capsaicin doesn't evaporate at the same temperature as alcohol, which is our solvent. We had to opt for aerosolization instead. So we ended up using a vibrating mesh transducer, which is basically like a plate with a bunch of incredibly tiny holes that act as a pump, and that can deliver a fine mist of things kept in their liquid phase compared to like evaporating it with temperature. Second, when you use these kinds of systems, one of the problems you get is that multiple channels have the possibility of cross-contamination. You don't want to output something that's warm and instead also pick up a little bit of the cool compound at the same time. In this, most of the time when devices are doing these kinds of things or using vibrating mesh transducers, they use conwicks, which is prone to cross-contamination. So you have to like use one per channel or per compound. In our case, we actually used separate tubings for each of the channels, which arrive to the vibrating mesh transducer, and then attach a small capillary tube at the end that's incredibly narrow and creates a surface tension of the inner liquid that won't allow other samples to backflow into another channel. What this ends up creating is a situation where a capillary tube can have a small droplet that's pushed out. It gets caught by the vibrating mesh transducer and then atomized, and it won't be like going into another tube, or other tubes won't be leaking out a liquid at the same time. That's what the illustration is of. Okay. Now, other things that are enjoyable about this is that you can easily access these reservoirs, either to refill things or to actually swap out the compound. This results in rendering temperature with a device that only requires 0.25 watts, which, as we saw, is a stark contrast to Peltier-elements, which use a bunch, or like hundreds of watts in comparison. So in our first study, we searched for compounds in literature that could easily be used in these kind of VR experiences, and selected 6 candidates that we each diluted in ethanol, aka Everclear in this case. So we had 3 warm candidates that were selected for their activation of the warm TRP channels, including thymol, a cayenne pepper tincture for capsaicin in this case, and methyl salicylate. We also had 3 additional compounds that were selected for their activation of cool TRP channels, including linalool, eucalyptal, and peppermint essential oil, which has a large concentration of menthol, which is why you get that refreshing sensation. Important to note is that 2 of these compounds, methyl salicylate and linalool, activate a combination of both cool and warm TRP channels apparently pretty equally based on literature. Now, to verify that the compounds were actually contributing to the perceived temperature and not the solvent, we used the solvent as a baseline. And in the study itself, participants inhaled 1 microliter of each compound and were asked to rate its perceived temperature on a visual analog scale. Now, we normalized all the results to the average score of the solvent as like a neutral rating. First, we found that linalool and methyl salicylate both elicited a huge range of temperature sensations because they activated both hot and cold TRP channels. Then we found that peppermint essential oil and thymol elicited the strongest perceived temperature sensations from participants. However, these compounds not only smell, but they're easily identifiable. So if you're smelling peppermint essential oil, it's pretty easy to say that it's mint. You're not very confused about the label for the odor. In contrast, what we're looking for in this kind of case, in this kind of situation, are compounds that optimize for two aspects. One, you want it to elicit a temperature illusion, and two, you don't want people to break the illusion by quickly recognizing what the odor is. Luckily, we found that another pair satisfied these criteria, particularly eucalyptal and capsaicin. Most participants weren't able to identify eucalyptal, though they could smell it. So they would smell something, but they wouldn't be sure how to label it. The nice thing is that none of the participants could actually distinguish the capsaicin solution from the baseline, as it was near odorless. And when you actually use capsaicin on its own, it is odorless itself. So what's cool is that participants were able to distinguish all these compounds with 1 microliter. And a very small percentage of these droplets actually have active compounds in them. That's incredibly small. So we're able to use these small quantities of eucalyptal and capsaicin to then test the illusion in virtual reality. So participants were placed in a VR environment and either had the temperature congruent stimulant or the baseline solvent. So for example, you would have a desert scene with the capsaicin solution or the baseline as a comparison. Turns out participants actually significantly felt warmer and colder with the stimulants than without, confirming that the temperature illusion holds up with the visually congruent information in virtual reality. So we put this all together with our prototype and created a VR scene demonstrating the full experience, and you got a snapshot of it at the start. So the user is in the cabin in the woods, warming up next to a furnace. They inhale capsaicin, which activates the warm TRP channels that we talked about earlier, creating an odorless warming sensation. Now, because there's kind of a storm outside, the electrical lines get destroyed and the door flings open, and our device renders the cool winds by emitting eucalyptal instead, which, like we saw before, activates those cool TRP channels and creates a cooling sensation for the user. Now, they're kind of cold. They don't want to stay in the cold forever. So they're going to go outside, try and find a generator and flip it on. At this point, because it's colder outside, we actually emit eucalyptal more frequently so that they inhale more of that compound over the time. Now, they find the emergency generator, flip it on, and as that generator warms up, it starts emitting capsaicin again. And not only do we emit capsaicin, we actually throw in a mix of a rubbery scent so that it kind of smells like burning fuel. And it's nice to note here that we're not only doing, again, temperature, but we're also mixing in smell. So as they come back in, they're going to close the door. And as the cabin heats back up, our device stops emitting eucalyptal and emits capsaicin again so that they feel the warmth come back in. And finally, they go back to the furnace again and warm up. Now, to conclude, we introduced a new way of creating temperature changes in VR based on an illusion. And what's nice about this is that this illusion is about 52 times more efficient than Peltier's, but it's still an illusion. So the current range of our illusion is pretty limited, but this provides a venue of investigating kind of synthetic superagonists. So these are things that are very strong for the TRP channels. Things like Islin for cold, which is about 50 times colder than menthol and doesn't have any odor at all. It has a limited area of effect right now, mostly to the face, but a couple of the participants mentioned the feeling expanding to the rest of the chest. The temperature sensations are tied to the user's inhalation, and users might actually unconsciously alter their breathing to minimize exposure to these compounds, like thymol, which is a very strong sensation when you breathe it in. And then our device relies on reservoirs, and as such, it's limited by a maximum capacity about 2 hours per reservoir. So if you use all three of them at the same time, then you have like a potentially 6-hour experience. That'd be very intense on a side note. However, it's worth noting that it provides an upgrade to any existing olfactory display to allow them to both render odors and temperatures and do it without too much energy cost. This is not only for VR, but could also be applied to mobile and AR contexts. And finally, while this is a promising illusion, we're keen on exploring how to expand this temperature illusion beyond the nose, which may offer richer experiences of temperature realism for VR. Now, I just wanted to acknowledge my co-authors again, Stephen Noggles and my advisor, Pedro Lopez. It was great working with both of you and continuing to work with both of you. And yeah, thank you. I'm happy to take any kind of questions. Yeah, that's the paper.